pleased to introduce Natacha Crooks, who's a professor at UC Berkeley, doing a lot of great work in distributed systems. Just became a Sloan Fellow, I saw. Congratulations. Today she'll talk about distributed trust ledgers are just a database, apparently.
So first, I'd like to apologize to Tim, because apparently every time I see him, I say that distributed trust ledgers are just a database, and now he has to hear an entire talk on it. So what I'm going to try and tell you is, convince you, is that many of the abstractions that we want from a distributed ledger, we could implement. If we start thinking about it, how we've thought about database systems for the last 20 or 30 years, we could actually implement them in a much more effective way, and we could simplify how they're used in practice. Now, obviously, I didn't necessarily know the background of everyone here, so there might be cases where I'm saying things that are painstakingly obvious. Likewise, there might be cases where I'm saying things that assuming that you know that you don't know. So feel free to ask questions, feel free to ask for any clarification questions. I tried to make it general, but it's never general enough. Now, usually I have a set of slides that talks about why applications need fault tolerance and why you should care about this. Given the audience here, I'm going to go, I remove most of that, and I'll just say one thing instead, which is I'll make the claim that every large-scale application implicitly trusts a specific component of the system, whether it's in software or hardware, for the reliability of computing data. So this fault-tolerant core provides the abstraction of a single failure-free component, the data store, and it's on top of that failure-free component that application logic gets implemented. And so effectively, applications use this fault-tolerant core as the root of trust to bootstrap application correctness. Today, I'm going to talk about distributed trust specifically. And obviously, you all are familiar with distributed trust. Otherwise, you probably walked into the wrong room. But I just want to define what I mean here. So there's two ways that I think about that people tend to define distributed trust. The first is as a deployment architecture that allows mutually distrustful parties to reliably and secure shared data amongst each other, even as a subset of parties misbehave. So you can think of it as, a set of banks, for example, that want to exchange financial transactions without a centralized clearinghouse like SWIFT. That should be obvious for the audience here. The other way is as a mechanism to replicate your data to enough other platforms such that the data remains secure even when one of those platforms gets compromised. So in this case, you might think of using a distributed trust architecture to replicate sensitive data across several major clouds, such that even if one cloud gets compromised, data integrity will be preserved. And I do think it's important to distinguish the two because they come with certain different assumptions. So distributed trust, and specifically the latter, is growing in popularity as a fault-tolerant core for several major services. So Signal, for example, uses it for key recovery. So when you lose your phone while skiing and need to restore your account, this may or may not be a true story, you can use this service to recover your key. ACL, the Azure Confidential Ledger, is Microsoft's distributed trust offering and is used for key transparency, code transparency, so on and so forth. And finally, of course, blockchains. So the particular model that I'm going to assume for the rest of the talk is looking at scenarios in which you have a well-defined set of participants from anywhere between, say, 5 to a few hundred. They each want to offer a shared service where you can store data and perform computation on it, very much like a database. And these parties want to maintain consistency and availability even when a subset of parties misbehave. And here I'll say that misbehaving participants are called Byzantine. We can use them interchangeably. And if that sounds familiar, well, then should. It's usually the type of guarantees that Byzantine fault-tolerant systems provide. At the heart of these append-only ledgers, there's this beautiful abstraction of a totally ordered ledger, or a log. So every participant in the system agrees on the same set of operations and the same ordering of operations. And these guarantees hold even in the presence of a subset of malicious actors. So in the example here, the 4 banks in the consortium all agree that there's 2 deposit operations followed by a transfer, followed by a withdrawal. Now again, not saying anything new here. But let's try and think about why this abstraction is so powerful. The reason why I think it's so powerful is because this shared log, whose validity is attested by all the consortium participants, can be reliably consumed, it can be ingested in order to reliably materialize shared state. For instance, Bob here on the left can ingest a copy of the log stored at Bank of America, execute the operations to come to the conclusion that account A has value 10 and account B has value 5. Similarly, Alice on the right can consume the copy of the log maintained at Chase and come to the same conclusion. And this shared state can be queried just as you would query a traditional key value store or database. Unfortunately, current BFT systems, I'm not going to say that they do not scale, because otherwise I've just invalidated my research for the last 5 years. I am going to say that they have a fundamental scaling limit. And there's 2 main reasons for that. The first one is that every replica totally orders every operation. This is clearly bad for throughput because execution is both sequential and redundant across all replicas. Moreover, reaching agreement usually requires several round trip of coordination, which can often result in high latency. And so the question is this fundamental? And obviously there's been many, many works to try and chip at this. And I'm simplifying here. But I would say that fundamentally, yes, this is a limitation, a scalability bottleneck that is fundamental in the current architecture. And the root cause to me is that we're building these systems with a rock-hard separation between the ordering layer and the materialization layer. The ordering layer currently is only about trust. It's basically saying, how can multiple parties agree on how to order the same sequence of bytes? The materialization layer, on the other hand, is all about semantics and data. It's saying, how can I execute those bytes or those operations to generate the database? And because the ordering layer does not understand the semantics of the operation, it just can't do any better. And that's a huge lost opportunity because we know that in practice, most real workloads primarily consist of operations that access completely different objects and thus don't need to be ordered with respect to each other. For instance, if Alice here on the left wants to buy ice cream and Bob here wants to buy a Ferrari, these operations do not need to be ordered with respect to each other because they commute. Independently of the order in which they're executed, they will generate the same state. And that's the point I really want to emphasize. And actually, you made this point earlier, just a few minutes ago, is that fundamentally we care about the state, the materialized state, not the log. The log is the mechanism through which we can reliably generate the state. So until a few weeks ago here, I had a joke that said, this held true unless you had a shop that sells both ice creams and Ferraris. It turns out that there is such a shop in New Jersey. So there goes my joke, but hopefully the idea remains clear.
I was waiting for the slide with the picture of the store that sells Ferraris and ice cream.
I promise I'll go back and buy another ice cream to take a picture.
All right.
So what should we do instead? Well, if you've got to take one point away from this talk, I want to be this. What most distributed ledgers actually try and want to build is a database. And by merging the ordering layer and the materialization layer into a single entity that is explicitly a database, but a database with decentralized trust, we can design a system that will scale better. And we can do this by taking advantage of the decades of research on scalable distributed databases.
So in this picture, should I think of the materialization layer, which sort of corresponds to the execution layer that we usually talk about? Should I think of that as Turing complete in your case, or not necessarily? Or
you can think of it as, in this case, I'm going to say equivalent to SQL, which is Turing complete.
Okay.
But the expressivity is going to matter for implementation, but not for any other things I'm going to say.
Okay. So maybe have in mind for the talk applications well expressed by natural SQL queries.
Yes.
Okay.
When you advocate thinking about distributed trust as a database, I'm wondering what's the alternative? What would you say is the not recommended way to think of it?
I think the over-reliance on a log as an executing operation sequentially in the log bakes the ordering requirement of the log with the semantics. Whereas a database explicitly acknowledges that there's going to be a mechanism through which you can achieve that equivalence to a serial order, but that's not the end goal. The end goal is instead the materialized state that provides you some guarantees, some consistency guarantees, both with respect to malicious participants, but also with respect to just the ordering in which you execute transactions. That's actually the point that I want to make here, which is that the key property that allows database systems to scale is called serializability. And serializability is this correctness criterion that I'm mentioning, which implements the abstraction of a total order. It guarantees an execution will remain indistinguishable from an execution in which every operation was executed sequentially, but does not enforce the physical total ordering. And so serializability specifically breaks down high-level operations in, like, say, transfer, into a set of physical read and write operations, so multiple sub-operations, that even though they physically execute as small units, overall, they will appear to take effect atomically and sequentially. And the mechanism that database systems use to enforce that is called concurrency control. So they guarantee equivalence to a serial order. Whereas I'll make the claim that right now in many distributed trust ledgers, we are interested in the reality, the physical log. Here we're trying to enforce the abstraction of the log. So this ability to execute sub-operations individually, as long as the overall execution remains appears sequential, allows for, I'll say, two properties that are key to scaling. So the first one is sharding. It's now going to be easy and natural to partition the object space, and a single replica no longer needs to process all requests. So transactions that touch multiple shards, distinct shards, no longer need to coordinate, and transactions that touch multiple shards obviously still need to run an atomic commit protocol. The second benefit is that independent operations, even if they access the same shard, but they touch different objects, can now naturally be executed in parallel. So even within a shard, we can get high concurrency, which is something that is challenging to implement in current BFT systems. Now, in any good system work, there's, I'd say, three properties that we care about. Performance. How many transactions are you going to execute per second? Usability. How difficult is it to execute those transactions as a programmer? And finally, the fault model with respect to what attacks or threat am I correct against. So we're going to want to build a scalable ledger by building a database. And what does this mean under those three pillars? Well, from a performance standpoint, we're going to want to allow non-conflicting operations to execute in parallel. From a usability standpoint, we're going to want to support general-purpose transactions and arbitrary SQL queries. So if I put my database hat, I tend to think that SQL is what people use in analytics, in OLTP systems, and we're going to want to try and preserve that legacy code. Now, I realize this is not how people have gone about implementing smart contracts, and this is probably a controversial take, but I'll say that the pillar of data management has always been SQL, and so we really wanted to preserve that. And finally, we're going to want to remain robust against arbitrary, aka Byzantine failures, with respect to a specific threshold of Byzantine failures. Most database systems tend to be separated into two layers. You've got a transactional key-value store that handles transactions and persistent storage. And on top of that, there's a query processing layer that handles complex queries like joins, like scans, so on. And so we did the same. We first set out to build Bazel, a transactional key-value store that supports general-purpose serializable transactions. And then we added a system called Pesto, which can act as a drop-in replacement for any standard database system. If you're wondering why we called it Pesto, well, as life gives you lemon, you make lemonade. So when life gives you Bazel, you make Pesto. And what I'm going to do in this talk is focus the main core of the talk on Bazel, the transactional key-value store, and then I'll touch on some of the challenges that you get from trying to build a complex SQL query processing layer.
You didn't, of course, answer the question of why it's called Bazel, right? You derived Pesto from
Bazel is an especially malicious Byzantine empire. Emperor of the Byzantine Empire.
Got it. Cool.
It's also a cute mouse in Disney. Depending on who you ask, you get different explanations for why we chose that name. So let's start with Bazel. And again, the key premise of the work is going to be database systems execute most operations in parallel. Let's see to what extent we can do the same here when we now have to worry about malicious participants. And in database systems, there's two general strategies. So the first one is locking. So as you access object, you're pessimistically going to take locks to guarantee that there are no concurrent conflicting accesses. If you get all the locks, you can commit. Now, this type of design is pretty simple, but in the BFT world, there's one big problem, which is that clients can acquire a lock and then just go get a coffee maliciously. It's not possible to distinguish a malicious client trying to acquire a lock and intentionally DDoSing the system from a transaction that just takes a while to execute. And those long-running transactions are pretty common in large-scale systems. So it's really too easy for clients to DDoS a system in the pessimistic world. And we cannot hold participants accountable. The other option is to be optimistic. That is to execute without locks, but validate in hindsight whether there were concurrent unsafe accesses. Now, optimistic concurrency control protocols are by design client-driven. It's the client running the validation, running the execution. So while in lock-based systems, the server is responsible for managing safety, here is going to be the responsibility of clients. And this is probably going to sound like a really bad idea, given I just said that clients can't be trusted, but we're going to see that it provides the right degree of flexibility to allow us to build it efficiently. So our mission in Bazel is, to summarize, to put together an optimistic client-driven scheme for a sharded and replicated database. And to do so in a setting where there are no bounds on the number of malicious clients. The only concession I'm going to make is that just as in all BFT protocols, the number of Byzantine replicas does not increase a bounded fraction, f. Now, Bazel specifically uses 5f+1 replicas, and just be patient to understand why. Normal BFT systems, or the majority of BFT systems, assume 3f+1. We're going to assume 5f+1, and there's good reasons for doing that, which will become clear during the talk. So to pull this off, we're going to need to start with a solid foundation to work on. And unfortunately, we're immediately off to a rocky start, because it's actually non-obvious what serializability even means in the context of Byzantine actors. Because we cannot constrain how such participants will interact with the system, we can't constrain the harm they'll do. So our first contribution in this work was to introduce a meaningful notion of correctness for transactional applications in a BFT setting. This is where Byzantine serializability comes in. So what we strive to guarantee is that the execution appears to a correct participant as indistinguishable from a serializable execution that only contained operation executed by correct clients. So framed differently, we submit that it's completely okay for a Byzantine participant to wreak havoc and violate ISA guarantees as long as every correct participant observes state that could have been generated by honest folks. Just to give you some more intuition, my flight was cancelled, supposedly because of thunderstorms. Now, I didn't personally see thunderstorms, but as long as there was thunderstorms somewhere that explained the behavior of United, that's okay, because there's an execution that shows United as honest. The other way to say it is, it's not a lie if you don't get caught. So as long as there's an execution that is exclusively honest clients that generates the same data, then because I can't distinguish the two, I'm going to say that it's Byzantine serializable. Now, Byzantine serializability talks about correctness, but it doesn't actually tell us much about progress. For example, a correct Byzantine serializable system could systematically abort all transactions. Now, that's correct, that's safe, it's just not a very useful system.
Sorry, quick question.
Yeah.
Is it also on the previous slide, every client should see the same serializable execution, or like different clients could see different ones?
All clients will see the same execution of conflicting operations. They may differ in the order in which they see non-conflicting operations.
Okay.
So same as a traditional serializability definition. Yes.
I'm just curious, while you're on the slide, what does it mean? I mean, appear indistinguishable from? I mean, what would be different if you just said they should see a serializable execution? There's no computational indistinguishability or anything like that here, right?
No. So in this case, we mean what's the difference between
like why would you just say
to
a correct participant should see a serializable execution? What would change in that formulation, if anything?
By indistinguishable here, we mean sees the same reads, so the same read values, and generates the same writes. So I think we were using the traditional terminology of consensus work when we use the word appear indistinguishable. But you're right that there's no computational indistinguishability argument. It's literally the same reads and writes. So that's safety. Liveness wants us to guarantee that we actually make progress. Now, the traditional notion of liveness in BFT systems is you provide a response. Here we want a slightly different notion because we want to avoid your transactions repeatedly aborting. That's guaranteeing a response, just not a very useful one. So to address this issue, we introduce a sort of more general notion of BFT correctness, of BFT liveness, which we call Byzantine independence. And Byzantine independence says that no group consisting of only Byzantine participant should be able to single-handedly decide the outcome of an operation, of a transaction. Now, achieving this property is not easy. In fact, it's not one that a leader-based system can achieve. And that's because the leader has undue control over transaction ordering and is able to inject conflicting transactions to influence the result. So again, we can't prevent your transaction from aborting because there might be a legitimate client that happens to access your data at the same time. But we want to make sure that Byzantine either clients or replicas can't force you to systematically abort. So now that we have sort of strong notions of correctness and progress in tow, the question becomes, how do we actually realize them in practice? And how do we do so efficiently? And here, there's a tension between performance in the common case and robustness to failures. So in the common case, you want to be able to process transactions as aggressively as possible to maximize system throughput. So this usually means favoring a concurrency control protocol that is optimistic and assumes that transactions will mostly commit and not abort. Now this includes protocol like optimistic concurrency control or multi-version timestamp ordering, for those of you who are familiar. Unfortunately, if you're not careful, this optimism can be leveraged by Byzantine actors to wreak havoc in the system, stab you in the back, and hurt throughput if we're not careful. So for robustness, we tend to want to favor pessimistic protocols. And so there's a tension here that we have to resolve. We want good performance in the common case, so we want to be optimistic, but we want robustness under failure, meaning that at times we want to be pessimistic. And this challenge is sort of reflected in Bazel's architecture. So Bazel consists of three core components: a concurrency control protocol, a commit protocol, and a fallback protocol. The concurrency control protocol allows non-conflicting operations to execute in parallel. The commit protocol is driven by the client and is going to aggregate replica votes to determine whether a transaction can commit across shards. And finally, the fallback protocol is going to ensure that an honest client can never be blocked by a malicious client from committing. Intuitively, think of an honest client waiting for a lock to be released forever, or waiting forever for a dependency to commit. The fallback protocol is going to ensure that an honest client can always proceed. So to execute transactions, Bazel offers a fairly classic begin, read, write, commit interface. So in Bazel, a client starts a transaction and begins executing individual read and write operations in parallel with other clients in the system. Transactions are what we say interactive, meaning that clients can dynamically issue the next read and write as they execute the operation. So here, the right way to imagine is not me sitting behind my keyboard and saying, read, what will I do next? Write. No, it's having those operations embedded in the application and then making point-wise calls to the database. So you might have all written a web app at some point, use something like a JDBC driver to talk to a MySQL database, and you'll do a mydatabase.starts, blah, blah, blah. You'll write a bunch of Java code or Rust code, whatever. mydatabase.read, do a bunch of code. mydatabase.write, do a bunch more Java code. mydatabase.commit. So by interactive transactions, we mean general purpose transactions that are embedded in the application code, and this is to contrast with stored procedures, which are pieces of code that you actually upload to the database, and the database executes at once. The reason for why we want interactive transactions is that database administrators really do not like stored procedures because it requires two different languages, it's complicated to upload and manage. This is usually where people tell me no blockchain would ever want that. That's usually the key distinguishing factor in our model and the smart contract model that people tend to challenge me on.
Sorry, for clarity, which is which? Which maps onto which?
So the general purpose interactive transactions is how people like to use database systems, where stored procedures are much more like the smart contract model, where you upload a stored procedure that will be executed server-side only. Okay. And there was a study a few years ago that said the database administrators really do not like stored procedures because of the lack of generality and having to maintain multiple versions of the code and having to use a different language. So in Bazel, writes are buffered locally until execution ends, and the concurrency control mechanism is going to detect at commit time any concurrent conflicting operations that happened on that replica during the validation phase. So I won't spend any time on this, but for those of you who are interested, the concurrency control that we use in Bazel is something called multi-version timestamp ordering that we adapt to be robust to Byzantine actors. And it strikes the right balance of optimism and pessimism. Now, don't expect you to know what it is. Won't talk about it more. You won't need it for the rest of this talk, but I'm happy to talk about it in the next week. Instead, I'm going to focus the majority of my talk on the commit protocol, which is once a transaction has finished executing, the role of this commit protocol is going to determine whether a transaction can commit based on the result of the validation check. Now, the validation check determines whether committing a transaction would violate serializability. That's multi-version timestamp ordering. And the commit protocol is going to somehow aggregate all those votes from the different shards and replicas to determine whether the overall execution is still serializable. Now, the commit protocol, and this is true for all distributed databases, consists of two main phases. So in the prepare phase, it must ensure that all shards agree to commit a transaction. And a shard is going to agree to commit a transaction if a majority of replicas in that shard agree to commit the transaction. At the very high level, a replica can commit a transaction if no concurrent conflicting transaction has already committed. The write-back phase is then going to aggregate these shard votes and either vote to commit a transaction or abort. Now in Bazel, the commit protocol is client-driven, meaning that the client drives the commit and there's no intermediate transaction manager. And the reason why we chose this approach is because we want the client to be responsible for its own destiny. We don't want the client to hand over responsibility to a transaction manager that could potentially be malicious. So since the write-back phase is basically just aggregating votes across shards, I'm just going to simplify my example to say that there's a single shard in the system, but it works for multiple shards. A shard consists of several replicas. In this case, we have 5f plus 1 replicas. So let's set f equals 1. One malicious replica gives us a total of 6 replicas. And let's say now that Mr. Bob here wants to figure out whether it can commit transaction T. Now, in the simplest case, all replicas vote to commit a transaction on this shard. So Bob gets 6 votes to say, I can commit. Great, fantastic. That's the simpler case. That kind of shows you the naive case. There's no concurrent transactions, and there's no concurrent conflicting transactions, and there's no other participants, malicious participants. Let's look at where it gets more complicated. So the first challenge in deciding whether to commit a transaction in this setup has nothing to do with BFT. Replicas can legitimately receive conflicting transactions in different orders, just because of the internet. And so could legitimately disagree on whether to commit a transaction. So for example, assume that you have a concurrent transaction T prime that conflicts with T. If a replica receives T first and then receives T, well, it might vote to abort T because it says, hang on, I've already voted to commit a conflicting transaction T prime, so now I can't commit T. But a different replica could not have received T prime yet, and so be completely fine with committing T. And you can end up in a situation where half of the replicas vote in favor of committing T prime and half vote against committing T prime. And this is just through benign reordering of transaction because of the speed of light being different across the world. Sorry, leading to different round trip times across the world. The second challenge is obviously that Byzantine replicas can lie. They can either vote to commit a transaction, even though they've already voted to commit a conflicting transaction. So in this example here, replica 2 could say, yeah, sure, I've already voted to commit T prime, but I'm still going to vote to commit T. And that would violate Byzantine serializability, meaning that we would end up in an execution that could not have been generated by honest clients executing their transaction. And they could also vote to abort a transaction, even though they have no grounds for doing so. So replica 1 here could vote to abort T, even though it hasn't seen any conflicting transaction. And that would violate Byzantine independence. Now, the final challenge is that clients can be malicious. They can either crash halfway through running the protocol, or they can intentionally delay sending the commit message, or potentially even send different messages to different people. And at that point, it becomes necessary for an honest client to finish committing the transaction of the faulty client. And we need that because we want honest clients to have their own destiny in their hands, so we never want them to be blocked by other clients failing to finish. And there's a challenge here. So in any BFT system, for liveness, if you have n total replicas, you could never wait for more than n minus f responses, because f of those people might have died, they might be crashed. So if you want to make progress, the maximum you can only ever wait for is n minus f. So in this case here, let's say that Bob waited for n minus f equals 4 replicas, so the first 4. It saw 3 commit and 2 abort. So Bob says, okay, I've got a majority of commit, let me commit, let me tell my users I've committed, and send an asynchronous write-back to notify the server. For whatever reason, the write-back messages gets delayed, Bob doesn't send it. So Alice says, well, I want to commit my transaction too, I don't want to wait forever for Bob. And it tries to finish a transaction for Bob so that it can execute itself. But again, Alice can only ever wait for n minus f responses. And so Alice happens to get responses from the bottom 4 replicas. And now Alice has 3 votes to abort and 2 votes to commit. Now the key issue is that we don't know whether Bob already sent the final write-back message to other shards. So Bob could have already decided to commit, and so Alice somehow needs to come to the same conclusion as Bob. So based on that, let me take you for the next 5 or 6 minutes on how we went about designing the commit rule and the abort rule. So what I'm going to focus on meat of this talk is what does this look like in the system, and specifically how do we guarantee Byzantine independence and Byzantine serializability given the challenges that I've just outlined. So the first thing that we have to worry about is how to maintain Byzantine independence. And as a brief reminder, Byzantine independence says that a Byzantine replica should not single-handedly influence the outcome of a transaction, which we're going to rephrase as a Byzantine replica should not single-handedly cause the transaction to abort. What does this mean? Well, it means that to abort a transaction, we need to ensure that at least one honest replica wanted to abort that transaction. If we have a majority of F Byzantine participants, this means that in order to abort a transaction in the way that always guarantees Byzantine independence, we need at least F plus 1 abort votes. That tends to be a magic number in BFT systems. So we have our first requirement. We can only abort a transaction when we have at least F plus 1 votes to abort. Now the second requirement that we have is Byzantine serializability. And Byzantine serializability says that if T and T prime conflict, they should not both commit. That's necessary to guarantee equivalence to a serial order. In order to enforce this, we're going to rely on some help from honest replicas. Honest replicas follow the protocol. So we know that if you're honest, you will never vote for T and T prime to both commit. So what we're going to do is we're going to force every quorum, every commit quorum, to intersect in at least one honest replica. Why? Because if every transaction needs a commit quorum to commit, and those commit quorums always have to intersect in one honest replica, that honest replica will never vote to commit both T and T prime if they conflict. Right? So if you know that T conflicts with T prime, then I'm going to really hope that if I make my quorums large enough such that they intersect in whoever is honest in this room, then we'll never commit both in T and T prime if they conflict.
Should the word intersection appear on this slide somewhere?
Yes.
Oh, okay.
And again, because we have only F Byzantine participants, as long as our quorums intersect in F plus 1 replicas, we know that one of those replicas will be honest. And so that replica will never vote to commit T and T prime. Second requirement. Now, the final challenge was linked to failures. Specifically, if Bob saw the first n minus F responses and crashed, or intentionally delayed sending a message, and Alice tried to finish Bob's transaction, we wanted to ensure that Alice can never come to a different conclusion than Bob did. In other words, if Bob voted to abort the transaction, or come to the conclusion they wants to abort, Alice should also abort, and if Bob said commit, Alice should also say commit. Meaning that the voting decision should be deterministic. Now, this is where, unfortunately, I don't have a great solution for you, in that we can prove that if you get fewer than 5F plus 1 commit votes or 3F plus 1 abort votes, we're going to need an additional logging phase to record the decision. And so we end up in a situation where our transactions commit in a single round trip in the majority of cases, but occasionally we'll need a second round trip to finalize the decision before telling the client commit or abort. So we end up with these 3 requirements for our commit rule. Requirement 1, you only abort when you have more than F plus 1 abort votes. You only commit when you have sufficiently many votes that your commit quorum intersects with all other commit quorums in at least one honest replica. And finally, if you get fewer than a specific threshold of votes, you need an additional round trip to record your decision such that other clients will always come to the same conclusion as you. Now, you might notice that I haven't actually told you the size of requirement 2, the size of the commit quorum. And the reason why I haven't told you that is because we're talking about intersection, that size depends on the total number of replicas in the system. So at the start of the talk, I said most BFT systems use 3f+1 replicas. That's kind of the standard threshold. So let's see if it works for us. Well, we want our commit quorums to intersect in at least one honest replica. So with 3f+1, this means that our quorum size has to be at least 2f+1. Why? Well, if you have 2f+1, you have 2f+1 here. If you do the math, if you sum them together, that gives you 4f+2. Well, we only have 3f+1 replicas in the system, so f+1 must be counted twice. That's kind of the rule usually to figure out quorum intersection. If you have 2f+1 and 2f+1, you overlap them, they need to overlap in at least f+1 replicas. Now, unfortunately, in a system with 3f+1 replicas, we're only guaranteed responses from n-f people. Namely, we're only guaranteed responses from 2f+1 nodes. And so we can end up in a situation where we happen to get 2f commit votes and 1 abort vote. And there we get stuck. Because we get stuck. We cannot commit because our 2f is smaller than 2f+1, so we're not guaranteed that this commit quorum will intersect with another commit quorum in an honest node. But we also can't abort because this abort vote might be from a malicious node. So we're stuck between either risking violating Byzantine serializability or we're stuck with risking violating Byzantine independence. Let's up the number of replicas. 4f+1, you end up in the same situation as the 3f+1 case. But now let's look at 5f+1. With 5f+1 replicas, you need a commit quorum of size 3f+1 in order to guarantee the f+1 intersection. Again, 3f+1 plus 3f+1 equals 6f+2, but we only have 5f+1 nodes, so f+1 of those must be counted twice. In a 5f+1 system, we're guaranteed a response from n-f nodes from 4f+1 nodes. And so we end up in a situation where we're guaranteed to either have a commit quorum or an abort quorum. So either from our 4f+1 responses, we're going to get 3f+1 commit votes, in which case we're good, or if we don't get 3f+1 commit votes, then we're guaranteed that the number of aborts that we get is at least f+1. And so we have the guarantee with 5f+1 nodes that we either have a commit quorum or have an abort quorum. And that's what enables us, why the requirements of 5f+1 commit, because we want to guarantee Byzantine independence. There's also a few other reasons for why you might want to have 5f+1. Namely, we have the ability to commit transactions in a single round trip. You lose that with 3f+1. And that matters if you're contention bottlenecked in a system. And so even though the number of replicas may appear higher, if you actually count the throughput that we can get, like the throughput per machine, 5f+1 ends up being cheaper than 3f+1.
You're saying because it's one round trip instead of two?
Yeah.
That's the difference, okay.
So I'm just curious, is that like a provable statement that you cannot do one round commit with 3f+1?
Yes, that's a pretty well-known result.
Yeah.
Yes. There's many results that suggest this is not possible when you have no leader and a fast path. I haven't yet seen, and we were actually thinking about that at some point, a formal proof that phrases it in exactly that way.
And I guess the same for 4f+1 as well.
4f+1, we actually looked at the Byzantine independence part. So I'm less sure about the 4f+1 result. The 5f+1, 99% sure that this is an impossibility result, but I haven't seen it phrased in that way. You seem to be...
In the BFT case, this has been written down a few times, but I'm not quite sure whether in the database setting is different, because the intuition you give is actually very different from the BFT one-round commit.
So in the BFT case, we haven't seen leaderless plus one-round commit.
Leaderless? I think we can, but we can prove even with a leader, you cannot do one-round voting commits. So leaderless is even only harder.
Oh, sorry, this is not one round always. This is the existence of a fast path.
Sure.
With
yeah,
a two-phase fallback.
Says. Yeah, even whatever good things happen, you cannot do one-round commit.
For context, it just so happens that several people have been spending a lot of time in the last 3 to 4 weeks specifically about one-round fast paths.
Yeah. For one round fast path, you end up needing 3f+1 replicas, like all of them. So this is a dizzy var work, or like others. This is the first one. For the 5f+1 leaderless, the fast path needs 5f+1, but I'm be surprised because I haven't seen a proof expressed in our way because we're actually looking at it at some point. We should chat offline.
Yeah, there's a lot of good conversations to have about this. Yeah.
The last part is that we know that clients cannot abort their own transactions or cause serializability violations, but clients can always stall. And so the fallback protocol is the mechanism that we use in Bazel to allow any client to drive the commit protocol, but not to change the outcome of the transaction. So you want clients to have the tool to drive the decision themselves, but we don't want them to have the power to either change the decision or come to a different conclusion than other clients. I'd say that the fast path is actually probably my favorite part of the protocol, but it's relatively involved, and so it has nice properties. In the common case, it requires only a single additional round trip to commit the transaction, which limits how harmful Byzantine clients can be generally. And the other benefit is that it only affects contending transactions. So in a traditional BFT system, when you have a view change, when you have a leader election, the system stalls. Here, the fallback protocol only affects transactions that happen to conflict with the transaction that you're currently stalled. Now, there's a number of challenges that we had to address, client equivocation, multiple clients live locking, but in the interest of time, learning about this is hopefully one of the many pleasures you get if I could convince you to read the paper. And instead, I'm going to give you some indication of how we do about performance. So we implemented Bazel and evaluated it using 3 common online transaction processing systems. So TPCC, which is a standard database benchmark that does shopping cart transactions. Small Bank, which emulates a small banking application, and WeTwist, which is a clone of a simple social network. And they experience varying levels of contention. And we ran Taper against 3 additional baselines. So the first is Taper, which is a crash fault tolerant distributed database that, like Bazel, merges concurrency control and replication. And the other 2 are BFT systems that follow the standard modular approach of how you might go about designing things today, which is that you layer a 2-phase commit protocol and a concurrency control protocol on top of a black box consensus protocol. So here we picked Hot Stuff and BFT Smart, which is an efficient implementation of PBFT. And we picked those 2 to be representative of state-of-the-art consensus protocols. So let's first look at the throughput for our workloads in a failure-free setup. And here, higher is better. So on the left, we found that Bazel is within 4x of Taper, so 4 times slower than a crash fault tolerant database. And that's a good result. That's something we were happy about. The main sources of overhead that you get is the need for signatures and larger quorum sizes to tolerate Byzantine failures. And signatures, they've gotten a lot cheaper, but they still take up space in your CPU, and so there's a lot less work that you can do, whereas Taper gets to use those extra cores to process additional transactions.
How many replicas?
So we have a total number of shards, and so Bazel uses fewer shards because it uses more replicas, whereas Taper uses more, can take advantage of those extra replicas to do more throughput.
No, I meant how many replicas are in these experiments?
I'll have to check, but I think it was 3 shards. With Bazel uses 5f+1, Taper uses 2f+1, Hot Stuff and BFTAP using 3f+1. So the standard replication factor. And I'm pretty sure, I'll have to check in the paper, but I'm pretty sure you use 3 shards for Bazel and scale it correspondingly for Taper, Hot Stuff, and BFT Smart.
But like, what was F?
Sorry, F was 1.
F was 1, okay.
So the good news is that we were able to get higher throughput than the baselines built around the traditional BFT systems. So between 5x and 3x respectively for TPCC. And the reason for why we were able to get better performance is that Bazel achieves much lower latency, which in a contention system translates to higher throughput. And this is because it has the ability to execute transactions in parallel. And the actual time it takes to commit a transaction is, in most cases, about 97% of cases, a single round trip in Bazel, whereas it takes at least 2 round trips in the other systems. Now, of course, so good performance is great in the failure-free case, but if it comes at the cost of catastrophic performance in the failure case, that's not good. And so we wanted to evaluate also what happens when clients misbehave and when replicas misbehave. So clients can try to fail in 2 ways. They can stall, they can start but not finish the transaction, the commit process, or they can try to equivocate, meaning that they can lie and send different decisions to different replicas. So I won't go into a huge amount of detail here about the results, I'll just give you a sneak peek. When clients stall, specifically when 10% of clients stall, then we're going to see about a 10% throughput drop. And the reason for why we see about a 10% throughput drop is because other clients have to finish the work for them, so they have to spend an extra round trip executing the fallback protocol. And it grows pretty linearly. So if you have 40% of clients stalling, you end up with a 40% throughput drop. The interesting result to me was the equivocation part. So in the equivocation part, we were really scared. We were like, okay, now the fallback is a lot more complicated than the equivocation part. Are we going to submit this paper? Is it catastrophic? And it turns out that with 40% faulty transactions, we see less than a 5% throughput drop. And that was a really surprising result for us. And the reason why we have this is that it's actually really, really hard for clients to get enough conflicting votes from replicas such that they can actually send conflicting decisions to people. So in most cases, replicas tend to be pretty much in agreement, in order. And because of that, it's actually really hard for clients to generate enough conflicting information to perform the equivocation successfully. Now, if we artificially allow clients to equivocate, then obviously performance becomes catastrophic. But in the real case, like in the realistic case, there's usually enough consistency between replicas and not enough contention that clients can actually equivocate successfully. So this is all I'm going to say about Bazel. Obviously, I'm here for the week, and this was a quick overview, but I'm very much happy to talk in more detail, and it's also the paper's available online. In the last few minutes, I'm instead going to move on to what we built on top of Bazel, namely Pesto. And the reason for why we built Pesto is because so far, I've been talking to you about point queries. Bob may want to withdraw some money, and to process this request, the Tompkins Bank or the Ithaca Bank or the blah bank who manages Bob's account is going to simply look up Bob's balance. It's going to do a GET request. Now, these are day-to-day operations that make up the bulk of transaction applications. And for the database folks here, this is when you access a primary index, for example. And database want you to do that. That's what they're geared for. That's what they are implemented efficiently for. But applications also usually want to perform range queries. That should stay range queries on top, sorry. So, for example, Bank of America may want to know how many customers it is serving in Berkeley. So using a key value store interface becomes really expensive to do that, because it must first read the entire databank of customers, then perform the additional aggregation to the client, and the client has to read all the intermediate data and then perform the computation to get the results. So implementing this range query is cumbersome for application developers if they only have point queries, because they need to manually specify the computation process, and it's also inefficient because we are going to issue many, many read requests when the result might just be 2 or 3 rows at the end. And that's especially expensive in a BFT setting because of the fact that you need some proofs to validate the correctness. So each GET that you do comes with validating a signature. So if you had a choice, we'd much rather execute such queries through an expressive query interface like SQL and rely on the backend to execute the query. Now, this looks easy to use, this is efficient. The problem though is that in Bazel, Bob, he's trying to execute his SQL query here, has no way of asserting the validity, the integrity, and the freshness of any one result. Because without retrieving the read set itself, there's no trivial way to confirm that a given replica's computation is correct. And even if we were using some fancy cryptography to validate the correctness of the result, there's no notion of freshness between 2 possibly different results based on a different state. So it's not just the correctness of the state, it's whether or not we're reading from, if we're given 2 different results, whether or not those which one is correct, which one we should use. Because those replicas might have processed transactions in different order. So the intuitive way to solve this problem is just to simply collect enough matching replies to guarantee at least 1 correct replica has sent it. Right? So if, for example, I get 6 responses and I have at least 2 replicas telling me that the result is 2 of my query, then I know at least 1 honest replica is telling me 2, and that's good enough. The problem, though, is that our inconsistent design, where replicas can process transactions out of order, comes back to bite us. Even correct replicas in Bazel may genuinely have different state. So here on the slide, the first key could have, the first replica could have processed for key 1 red, red, blue, and may still be waiting for light yellow, whereas the state 2 could have already seen light yellow and be waiting for red, red, blue. That's perfectly okay. And this means that we can't actually guarantee we will ever see matching results. And that's going to kill liveness. Now, the alternate strategy is obviously to return to a total order where we order every transaction. But I've just spent the last 45 minutes telling you that we want to not have a total order. So it'd be kind of a sad way to end the talk if we just say, well, we'll go back to a total order. So what can we do instead? Well, instead we're going to cheat. And as any good cheater, I'm not going to reveal all my secrets, and I'm just going to give you the high-level idea and tell you, please do check the paper or talk to me afterwards for the details. In reality, we don't care for the state to be consistent. Instead, we only care for the state to appear consistent to clients. So we only require consistency for the query that we are currently making, not for any arbitrary query that we could possibly be making. And individual queries don't normally touch the same state, the whole state, sorry. So it's much cheaper to bootstrap consistency for just the query that we're making than it is to synchronize all replicas all at once. And there's a bunch of challenges in doing so. Let's say that Bob sort of sends the queries and waits for responses. If we're lucky, replicas already match, and we have nothing to do. And it turns out that that's the case the majority of the time. Because in practice, again, most operations commute, and so replicas don't diverge a whole lot. You have to get unlucky to catch a point where they diverge. When replicas don't match, however, then once again, we're going to double down on our client-driven ethos and basically allow the clients to create their own luck. We're going to have Bob propose a consistent state for the query that he's making himself. Replicas can then synchronize on the missing data and materialize the particular state on demand to guarantee consistent execution. At a high level, this solves the freshness problem because we now have the guarantee after this potential extra round trip that replicas will be in a consistent state. But obviously, the devil is in the details. So specifically, we're going to need to ensure that the client will always be able to propose a valid snapshot, okay, one that is serializable, as well as fresh, okay, not a snapshot that's infinitely far in the past, as that can cause aborts. So specifically, we don't want replicas to be able to trick, or the client to be tricked into proposing something that is too stale, or that does not represent a consistent state. Second, we're also going to need to revisit how we do concurrency control. So one of the main problems we faced, and we're surprised by that actually, is that range queries and optimistic concurrency control typically don't play well together. Optimistic protocols have a validation phase, like the one that we use in Bazel, and that says that no writes should interfere with the reads that I just did. And they do this by sort of tracking the rows and the versions that we access and aborting if we miss something. But if we're doing a range query, then we logically read literally everything. We might have filtered a bunch of stuff, but we logically read everything. And so now it means that literally a single write can invalidate our read of 2,000, 3,000 transactions. We don't want to acquire a giant lock on this because this would kill performance, and locks are bad for reasons I said before. So we need a new way to reason about concurrency control for range queries in the optimistic setting. Now, the way that we approach this is by a technique called an adaptation of something called precision locking, which I'm happy to talk about offline. Instead, I'll just give you a very quick snapshot in the last minute of the numbers that we got. So the thing that we were really excited about is that we were able to run complex SQL benchmarks unmodified. So we took, again, some standard SQL benchmarks, something like Orchard, Mark, and Seed, and those have fairly complex joins, fairly complex query results, and we were able to run them unmodified with decentralized trust. Our system, our BFT system, could take existing code, run it, and so it's fully SQL compliant, where fully is the work of PhD students. Please don't run this in production yet. So the big asterisk is obviously, I'm sure there's corner cases that for which it doesn't work fully. The good news is that we were able to continue getting 3 to 5x better performance than the prior layered approaches. Again, because we're able to get much more concurrency, scale the size of the latency down such that we could get higher throughput. What was promising is that depending on the workload, we were actually comparable to a commercial database like Postgres. So in cases where we had high contention, we were able to actually almost match Postgres performance. Whereas in cases where Postgres was a CPU bottlenecked, again, we were limited by the fact that we had to do a lot of cryptography and additional replication, but we were actually within 2x of Postgres, which to us was a very promising result. Now, this is all going to say for Bazel and Pesto. Obviously, I want to acknowledge that the people who have done most of the low-level work are my PhD students. Specifically, the Pesto and Bazel is primarily the work of Florence Ferripaya, his PhD thesis, and he was supported by Neil Giridaran in the Pesto work, who did much of the engineering work related to taking an existing SQL query engine and adapting it to the BFT setting. Before I finish, I just want to highlight a couple of other projects that I think will be of interest to here. Specifically, we've done a lot of work on looking at how consensus protocols interact with realistic networks and how we can improve the robustness of consensus protocols in that context. We've looked at how to design distributed trust protocols where you do use trusted enclaves because they're pretty good most of the time, but you are wary of trusting them always because they can stab you in the back and vulnerabilities can be found. And finally, we started revisiting how we think about failures to begin with. So, failures are inherently probabilistic. I have a 3% failure rate on my disk. I trust you with about 15% probability, where 15% might be determined by some risk analysis somewhere else. How can I express this notion of probability into consensus, and how can I refine my fault model such that it's smarter than just f equals 1, f equals 2. Whoops, we had f equals 3. We're toast. So with that, hopefully I've convinced you that append-only ledgers are just databases, and if I haven't, I've got a whole 5 days to do so. So thank you. Any questions?
I think a lot of the room's probably trying to map this to kind of like, consensus stuff that, we're already out. So one I'm just trying to think about is around like timing models, right? Which, partial synchronous kind of stuff, which I often think of as the most common origin, the 3f+1. So how should I think about this more from a database?
This is all in the partial synchrony model. There is no difference to the partial synchrony.
Right?
Sorry?
So is that, and then in distributed database applications, should I think of these shards as being historically in the same data center? And this is what I'm trying to think about. Why partial synchrony here?
Why partial synchrony? Because we need liveness. And in order to do that, there is one point where we need to elect a leader. We have a view change. We need to elect a leader to get around live lock. And so you need enough people to be in the same view in order to have the leader decide. So in order to have liveness, we end up deep down the stack having to elect a leader to get away from live lock. The leader doesn't get to decide and order transactions, but it does get to finish other transactions. And so that's why we get back into the partial synchrony model.
Maybe a different way to ask the question. I mean, does anyone ever look at the synchronous model in the distributed database context, or that's just like timeouts are just out of the question? Or
I think it depends on the systems that you want. So for example, there are systems that are based on chain replication, there are systems that are based on primary backup. Those effectively assume a synchronous model.
Okay.
The systems that use Paxos at some place, if CockroachDB has a Raft implementation, TiDB has a Raft implementation, end up inheriting the same limitations and benefits of the partial synchrony model.
Okay.
This is more like me trying to understand the protocol better. But so if we have a 3f+1 quorum saying this is to be committed, and then an f+1 abort certificate for it, in this case, how would it be resolved? If the client is honest, this cannot happen because f+1 abort certificate cannot happen. Like an honest person won't see a conflicting transaction by an honest client. But if you're a malicious client sending one abort message to that one honest and then to f+1 honest, it's sending a commit, then how is this resolved? So
this is why you need a second phase. Because it is, so what would have happened in this case is that you had 3f+1 people say, commit a transaction. f+1 people say abort a transaction, and so that node in the middle that happened to see was able to trick the client into forming both a commit quorum and an abort quorum. At that point, both are safe as long as you do a extra round to ensure that whatever decision the first client comes to, other people will also come to the same decision. So in this case, there's one, your commit quorum is large enough that you know that other people will intersect, and your abort quorum is also large enough that you're not violating Byzantine independence. The key thing here is ensuring that subsequent clients will come to the same decision as you. And so in this case, we're going to force the client to do an extra logging phase to say, hey, look, I have decided commit, and that logging phase is going to intersect with all future commit and abort quorums of other clients, and that's what's going to ensure the determinism.
Who is committing in the system? Both clients and replicas, or just the clients?
Clients commit. Replicas, when they do the fallback, can finish a transaction on behalf of a client that solicited it.
So replicas commit one round later than the client. Is that right?
Yes, so the way that the fallback works in our casing is that the client is going to try and finish a transaction, is going to wait. Some point is going to say, well, they've got something that I'm blocked on, I'm preparing transaction, and is going to trigger a fallback. In the easy case, it's just going to get matching results. In the more complicated case, it's going to get responses from replicas that suggest there's been some inconsistency, or maybe there's been a previous fallback, or maybe there's been equivocation. And at that point, the system is going to elect a fallback leader internally, where the fallback leader is going to aggregate the votes, and based on the votes that already take place, is going to finalize the decision before responding to the client.
The questions for Natacha?
Thanks.